In this example, we have bivariate data of time and the number of bacteria growing in a petri dish. So we have 5 pairs of values. The data is then coded using x equals t and y equals the logarithm of n. Part A, find the product moment correlation coefficient for the coded data, not the original data. The product moment correlation coefficient only measures linear correlation, and this data certainly doesn't look like it's growing in a linear fashion. The values of n are growing faster and faster, so it looks more like an exponential model here. And in fact, when you look ahead to part B, you can see where it mentions an exponential model. We need to decide whether that would be a good fit for this data. Well, looking at the numbers, that does seem reasonable. It's definitely not linear. If you drew these on a scatter graph, you wouldn't expect to see a straight line. So find the PMCC for the coded data. So go into my calculator. Make sure you enter the coded data into your calculator. Now I've just done another calculation. Numbers are still there. So a quick way of getting rid of them is go to Option, number 2, Editor, and then number 2 again, Delete All. So I'm going to put in the first column the x values. Well, they become x values after being coded. So t values become x values. So 1, 2, 4, 7, and 9. 1, 2, 4, 7, 9. 1, 2, 4, 7, 9. And then in the y values, we're not entering the original data, we're entering the coded data. So we want log 20. We don't need to enter a base. When you see this, this means log base 10. So log 20, log 38, log 74. Notice we don't actually need to close the brackets on the screen. We can just press equals now, and the calculator sort of closes them for us. Log 498 and log 1552. So here we have our coded data. We now need to find the correlation coefficient. So Option, regression calc, and it's the value of R we're looking for. And this turns out to be very, very strong correlation, 0.996, very strong positive linear correlation. So the 3 significant figures, 0.996. So part B, with reference to your answer to part A, state whether an exponential model is a good fit. Well, when we code data like this, by either logging both the 2 initial variables or just logging one of them, if the coded data then fits on a straight line, then our original model fits an exponential curve, or an exponential model. So in this case, you can say since R is positive and very close to 1, there's a strong, you could say very strong linear correlation between log n and t. So when that happens, we know the original data would fit an exponential model. So the points for the coded data, if we drew them on a scatter graph, would lie very close to a straight line. And from earlier in the chapter, we know that means an exponential model would be a good fit. So we're answering the question, state whether it's a good fit for the data. Our answer is yes, it is. And we have referenced the answer to part A as well. Just as a little extension, if you were to draw the original data on the scatter graph, this is what you'd see. And it does seem to have an exponential curve. But to be sure, we can log either both variables or just one of them. In this example, we logged just the n values. And if you drew a graph of the coded data, this is what you get. As you can see, very close to a straight line, hence the very strong positive linear correlation. So because the logged data fit a straight line, then the original data fit an exponential model.